Weirdly enough, we will never run out of fresh water. And I think that surprises a lot of people because you think of fresh water as being this very kind of precious commodity. But from work that's been done over the last couple of years, the amount of fresh water globally has actually increased compared to the amount that's been lost. So in terms of quantity, we will not run out of fresh water. We do have these concepts called planetary boundaries, which suggest that a global use of fresh water. But that doesn't really make sense because the problem with fresh water is that it's so unevenly distributed around the world that some places are rich in the resource and they'll never run out, whereas other places the resource is very limited, and that is where the problems can arise. And so instead of having a planetary boundary, what's probably a better way to think about it is to have a regional boundary, or to think about fresh water in terms of environmental water flows. So we should be looking at fresh waters in the unit of, say, the catchment, and that is the lake and all the rivers that flow into it. If we take out more water than flows through a river in a month, then that is going to pose problems for freshwater security. If you take out a lot of water that flows for many months from a river going into the lake, then that is clearly very problematic. And in that situation, then we will see an example of when fresh water becomes limiting, and that's when we have to take care. And there's some very good examples of that around the world, such as the RLC in Uzbekistan and Kazakhstan, but also Lake Urmia as well in Iran, which is following a similar type of fate, where 40,000 illegal wells are extracting water faster than it can flow into the lake.
Famous conference, 2014 in Singapore, where about 800 people came there together. The person who was opening this conference, organizer Nicolas Georges, started that conference with a sentence: "The time of metamaterials is over." Everybody was shocked why we came to Singapore, to hear the time is over. And then he said, it's the time of tunable metamaterials. Materials that you cannot build once, but you can tune and change in real time. And my answer to that was that electrochemistry can provide you quite a lot of that. And we started on one front. It was actually before that, because there I already was giving a keynote lecture about what we had at that time. We started first with liquid-liquid interfaces. Oil and water don't mix, but if you drop nanoparticles there, these nanoparticles will settle at the interface to block the interface between oil and water, because oil and water hate each other, right? The role of nanoparticle will be the same as peacekeeping troops between two ethnic groups which are fighting with each other. And if those ethnic groups hate each other more than the peacekeepers, right, then it will be a stable position for peacekeepers. If they start to hate peacekeepers more than each other, of course there is a problem. The particle will be gone. Anyway, that way we have the same situation. We have particles then settling on the surface by themselves. But the particles, when we speak about metallic nanoparticles, we need to protect them against fusion in the bulk. They fuse due to the so-called van der Waals forces. And if you just let them do it, you will have a big blob there of metal and will fall down and you cannot use it. So what you do, you cover them by special molecules, they're called ligands, which will have terminal groups, which will dissociate and will be charged. So such kind of nanoparticle may have 900 charges, elementary charges. So these particles are, people call them functionalized, not to come close to each other. Now, but they come to the surface, and if they hate each other, what's going to happen? They will try to be away from each other. But still they want to come. So the same analogy, for instance, like in this country, imagine the queen should travel in some cortege, and then the people stand there and want to see the queen, right? And of course, at the beginning, they don't come close to each other because they don't like it, but in the end, they will be densely packed. How you can regulate the interaction? Very simply. You can, first of all, change the charge on them, so will repel. You can go to that charge, they still don't fuse in the bulk, but the minimum is possible. Also, you can change electrolyte concentration, which screens all electrostatic interaction there, and because of that, they will not. They will be able to come closer to each other, and you can do that. And the first thing that we've done, it was to show that you can get a giant Raman effect in such system, and the beauty of that system that the molecules can come from oil side, from the side of the water side, different kind of molecules, and we could see huge enhancement. We could detect, let us say, one molecule per 5 nanoparticles with such proportion. And that was our first paper on the subject in Nature Materials about it. And that kind of was very interesting for different kind of analysis, in the first place of wrong substances in their presence, which are yet not damaging and dangerous for people, but you can get a signature of them. But then my dream was to have an electrochemical system, and that work was done, what I mentioned with Searson, like that. That was a wonderful cooperation between me on theoretical part and Joshua Edel. It's a champion of microfluidics and analytical science in our department, and we worked together on that, and we made that system working. And then the idea was, okay, and if we apply electric field or apply voltage, put this system between the two electrodes. You have the liquid-liquid interface and two electrodes here. One is positive, another negative. This will be water, this will be oil. So particles live in water, they like water, they don't live in oil, but they come to the surface to block the interface. And what you can do when you apply, for instance, make that electrode more negative, so you'll push negatively charged particles to occupy the surface densely, more densely. And if you charge your electrode positively, they will all leave the surface. So what's the fun here? Why? Why it's interesting? First of all, we had a very simple theory, which actually working very well, that if you have an array of nanoparticles there, and if it's dense enough, it will reflect light. It will reflect light much more than, for instance, the same amount of metal if it were continuous sheet. If you take them and build a continuous sheet of them, it will not be, it will be still transparent. But due to interesting this resonance effect there, they reflect light. And you can see the system as a mirror. And we had the theory which was describing the spectra of that reflection, depending on the distance between particles, depending on the, essentially, the density of that array. And that was finally realized in our new paper in Nature Materials about it, where we could see that you can really, you can convert the mirror into window by half a volt applied voltage. There was a big team, there are many authors there, that was cooperation with another professor, our electrochemistry champion, Anthony Kuthernuk, and 3 of us were leading that project, and there were young enthusiastic people like my postdoc Devabrata Sigdar, he is now in India but will join us again, and Union Montelongo, who is back to Mexico, absolutely international team like that one. So we have shown that that mirror works. You can have. The problem with that thing was that mirror is very slow. Why? Because when the particles are let go into the big bulk, they need to return. And how they return? If you have a lot of them, high concentration, of course there will be not a long path for them to come to cover the surface, but then your solution will be colored, which is not good. You want to have a transparent window relative to the mirror. And what is happening in that case, what we have investigated, what is the speed for them to come? And the time to reach that is inversely proportional to the square of the concentration of nanoparticles in the bulk. So we know how to make that kind of time fast. In our Nature Materials paper in attachment, we have a movie when you can see, for instance, You can see a reflection of a coin, of a £1 coin, which is when you change voltage, becomes a transparent, and you see £10 note underneath, and it's converted from one state to the other state. Very beautiful, became very popular, discussed everywhere, but the problem that is a very slow process. It was not shown in real time. And in order to do it fast, we need to do it with very thin layer. What so far has been achieved was in a macroscopic electrochemical cell, and now we work on nano or microscopic electrochemical cell, very thin, so that concentration will be increased not because there will be many particles, but the path for the light will be small. And that will allow you to reach, according to our estimates, to about a millisecond switch from mirror and window. The other thing, you go from liquid-liquid, which may be very interesting for CERS because you capture different analytes and so on. But for practical application, if you want to have a mirror window in a skyscraper, and the whole idea, how you can sell that idea, that if you have such a kind of thing, then you can save a lot of energy in the countries with hot climate. You leave the office, switch, 1 volt, it changes, becomes a mirror, and you save a lot of energy, right, on air conditioning. You know, in the United States, they spend more time on air conditioning in summer than on heating in winter, overall the country, as far as I heard about. But it's definitely the case in real countries with really very, very hot climate. So the kind of thing, vertical liquid-liquid interface, the first blog on that paper was, but they will not be able to make a vertical interface. In principle, you can. You have to functionalize one glass, the other glass, that will look like water, that one. You have to equilibrate their weights. Because what may happen, you created such system and then they will segregate and the interface will be like that. What is going to happen? The people who bought your windows will come and kill you, right? Anyway, we work on a solid, transparent electrodes at the moment. As described, we developed theory for that as well, and also in microscopic dimension of a cell, which will allow to gather those particles and put them away on a transparent, solid electrode. And then there is no issue that of any segregation. It could be vertical, could be horizontal, could be anything. So that is one kind of example of electrochemically controlled optical metamaterials. But that is a proof of the principle and the case also to interest a lot of people who are working on different metamaterials with different functionalities, not only plasmonic functionalities. If we can use electrochemistry to modify these materials. We can talk also about other non-optical metamaterials, what I call electromechanical metamaterials. And there are many examples of them, and we're also working on them here. For one of those systems is, for instance, the key element for microrobotics. This is a sheet like a capacitor with bendable plates. And then when you can polarize those plates, and if in between those plates you have a polymer, and in this polymer you have one sort of ions that can move. So, for instance, positive. You polarize this negatively, it's positively, and your ions will go to one side. They will exert kind of tension here. So the system tried to expand here and shrink here. So you will bend. You change polarity, you will bend that way. So you will have a hand which is going that way and that way. That's called electroactuator. One thing. There are, it also has the essence of that electroactuator is a story of electrical double layer, how ions are accumulated. I would say modern ionics, or ionic metamaterials, like that one. There are reverse actuators. For instance, you press your electrolyte in the pore, which is an electrode, which is polarized, and then when you get that electrolyte inside, the capacitance of that interface increases because there is a double layer, contact of the double layer with the surface increases. And so if you keep it under constant voltage, then there will be current going there because capacitance increased. You press it back, if the liquid goes back, then in that case your current will flow in the opposite direction. This is the principle of electrical shoe. Yes, I'm showing that for its generation of electrical current from walking. And there is a lot of interesting stuff happening in this area. One of the champions of that is Tom Krupenkin in University of Wisconsin, who is doing, he patented first things like that. We're working on the theory of rather involved systems like that. So it's also kind of metamaterial. You walk, you generate electricity, you charge your mobile phone, and of course it can be, the market for such kind of applications is huge. As Krupenkin told me, it has not yet taken off because there is no understanding between the shoe companies and the electrical companies. When that understanding will come, so there will be a lot of things done in that way. These are just a couple of more examples, but there are many more. Just one thing, why an array of nanoparticle will reflect light. There will be some transmitted light, of course, but a lot of it will be reflected, so you can see it with your naked eye that there is a mirror. Well, I will not give you any kind of mathematical foundation for that, it's all published, but give you a historical analogy. 300 Spartans, when they came and to stand in front of the Persian invasion, they came and standing in the narrow path of them, they were able to stop that invasion. Can you imagine what would happen if those Spartans were spread over Sparta? Of course, the Persian would not notice them and went through that. Something similar is happening here with nanoparticles. When they're close, there are resonance phenomena, they're very strong, they excite together, and excitation interact with each other, and there are interesting resonances there, and there is that reflectivity of light. So that's my second military analogy.
One of the things I worked on was the discovery of the Higgs boson at the CERN's Large Hadron Collider, which was announced, what is it now, 7 years ago, 2012, time flies. That was a really significant moment in physics. It had a really big impact on the field and beyond, actually, and for a number of reasons. So I guess first of all, starting with the physics, we have this rather wonderful theory of the fundamental forces and interactions of nature that we call the Standard Model. But in its most naive, I mean, it predicts infinitely small particles interacting with each other that can build up to make the world around us, and it's an amazing kind of achievement mathematically and scientifically. But in its most naive form, it doesn't work because it doesn't allow these infinitely small particles to have mass. And we know that they do. And so the way around that, a mathematical trick that was invented actually in the early 60s, even before we knew about all the particles of the Standard Model, was to introduce a kind of background energy quantum field which fills the whole universe. And it's by interacting with this quantum field that particles acquire mass. So it's, in a way, it's not something they have of their own, it's something they get because they're kind of sticking to this field. And then you ask yourself, well, that's a nice theory, it makes the maths work, but I don't really believe it until I see a bit more evidence. I'm not a theorist, I'm an experimentalist, so I'd like to see a bit more evidence than just, oh, the maths looks good. So how do you tell that there's something filling space? I mean, you can tell, for instance, that there's air in this room, many ways, but one way you can tell is that the sound waves from my mouth can travel through it. So I'm making pressure waves in the air and they travel to the microphones and pick it up. That wouldn't happen if there was no air in the room. In a vacuum, no one can hear you talk about physics. The Higgs boson is the analogy of the sound waves, but for this background energy field of the universe. So if this background energy field exists, if you hit it really hard, then it will wobble. And it's a quantum field, so a quantum wobble is actually a particle, it's a quantum particle, and that's the Higgs boson. So the impact of the Higgs boson was much more than, oh, we've just found the last particle of the Standard Model, which indeed it was, that's true as well. But the main thing was it proves that this background energy field of the universe is there which vindicates the kind of idea about how all particles get their mass, the mass of fundamental particles. So that's a huge kind of impact. It was a massive prediction of the Standard Model of something completely new that turned out to be right. So it's a big confidence builder in our understanding of nature in that sense. But another way it has an impact is that it was the last particle of the Standard Model. So all my physics career, we've had the Higgs boson on the horizon that we think this is there, but we don't really know. Now we know. So what's on the horizon now? What's going on now? And I have in my the way I think of physics as an experimentalist, I think we're explorers. I think that when you look at the Large Hadron Collider and it was studying nature at these high energies and small distance scales that we've never seen before, I think of it as like we're landing in a new country and we're exploring this new country and we're wandering across it and seeing what we can find. And for all my career, we've had the theoretical physicists have drawn a map and said, this is what you should find, go and look. And we went and looked, and indeed there was the Higgs boson, it was there, they were right. Now they made up some other things that they said should be on the map that would be beyond the Standard Model, and they are not there at the moment. And actually they have no real map anymore. We're really on the edge of the map. So to my mind, that's both a nerve-wracking but also really exciting period of physics, because we're really into the unknown now. And a lot of the ideas of what should have been found at the Large Hadron Collider, things like supersymmetry or extra dimensions and things that maybe there were arguments that they should be kind of found along with the Higgs or near the Higgs, they're not there. I mean, they might be. We've got a lot more data to come, but they certainly weren't as obvious as many theorists told us they would be. So we're really off the map. We're really sailing into this ocean now, kind of leaving the islands behind us. And for the first time in my career, experiment is ahead, actually, and I really like that. It's kind of, I do find that very exciting. So that's the impact on the field of physics, on the field of particle physics. It's been huge. It's both vindicated these real important fundamental mathematical ideas behind the Standard Model, and it's also taken us beyond the Standard Model in the sense that we don't have a map now of what else we might find. And we have very good reasons to know that the Standard Model isn't in fact the whole story. It's not a theory of everything. There are various things that can't be understood within it. There's evidence from astrophysical observations that there's more matter in the galaxies than we observe, for instance. And we postulate something called dark matter to explain that, but it's not in the Standard Model. So it might be out there beyond the map, and that's where we're sailing now. We also don't understand why there isn't pretty much the same amount of matter and antimatter in the universe, and that doesn't seem to be explainable within the Standard Model, and maybe the explanation is out there somewhere off the map where we're sailing. So that's a huge impact. It really changed the way we think about experimental physics in a way. And the impact of that is still being absorbed. The theoretical physics community is still absorbing the information that a lot of their expectations were not correct. Other ones might be, but might be harder to find than others, or maybe we just need some better ideas to explain these things. Maybe the old ideas pre the LHC were just not right, and these are arguments that this physics should be near the Higgs, things that we call like naturalness and stuff. Maybe they're misleading arguments. They're not. Maybe nature doesn't have to behave the way we expect it to, and we're really we're in the realm where the unexpected may show up. The other impact of the Higgs, I would say, the sense of the word impact. I mean, what I've talked about now really is its impact on our understanding of nature in the sense of particle physics. But I was sitting in my university department now in University College London. We saw a huge change in the attitude of people to physics with the discovery of the Higgs. I was writing in newspapers and doing some TV programs and things around the time, and the excitement around that discovery, the general public were excited about it in a way that I didn't really expect, because it's quite hard to understand what it means, but somehow it caught people's imagination in a way that I didn't expect, and that changed the perception. I think it wasn't just the Higgs there; it was this huge machine at CERN and the excitement of the technology and all the things that go with it, and the international collaboration and everything. but somehow the Higgs discovery raised the profile of all of that, and raised the profile of exploratory science and research in general in a way that maybe it's not very common. I mean, it does happen, but gravitational waves was another big discovery that had a huge impact. I think the Higgs was one of those things, and I think we're still seeing the knock-on effects of that. So okay, it's gone out of the public eye as much now. These things don't go on forever, obviously, but still CERN is better known than it was. Particle physics is better known than it was. And amongst the people that really matter to us in universities a lot, which is the young kids who are deciding what to study, more of them are deciding to study physics again now, and I think some of that is because of the Higgs boson. There was a feeling that maybe the physics was the science of the 20th century, and maybe the 21st century belongs entirely to, say, biology and the life sciences and things. And I think it changed that perception, and that there's still exciting new physics, new research to be done, exciting technologies being developed as well, and important new knowledge to be gained in physics. And I think, although the public interest obviously died away, we didn't go back to the same place. I think we've stayed in the place where physics is seen as more relevant, more interesting, more exciting than it was before. So and that's because it had a real impact on the science. It also had this impact on the wider society, I think, which was very important. The future directions is, of course, the fact that we're off the map now means that they're a lot less clear than they were. So we really knew that we had to build the Large Hadron Collider, because we knew that if the Higgs existed, we would find it, and if it didn't, it was important to prove that it didn't. There's a much more active discussion now about, okay, we've got this open landscape here, what's the best way to explore it, how do we do it, what's the most efficient way? So right now, actually, there's a huge discussion going on. CERN people associated with CERN have put together some proposals for even bigger colliders, of linear colliders and big circular ones, 100 kilometers this time, better magnets, better detectors. All of that would be exciting and will do great science. But is it the best thing to do? We don't have a guaranteed discovery, if you like we did with the Higgs. We're really exploring. Are we really prepared to go to all that effort to explore? Personally, I hope we are, because I think the exploration is actually more exciting than just going and kind of proving a theory that was already there. But it's to be discussed, and a lot of it depends on the technology and how cheaply and how expensive it is to do it, and whether the political will and the collaborative will is still there to do it. But I hope something along those lines happens. And then there are also experiments, the neutrino area. Neutrinos changed the standard model completely, because in the original version they didn't have mass, and now they do, but we don't know whether that mass comes from the Higgs. So there's good physics to be done with that too. But what we know we will do, I mean, in the next 10 years, that will definitely happen, is we will be exploring the properties of the Higgs boson in great detail, which may not sound, doing something in great detail doesn't sound super exciting or exploratory, but actually the Higgs is such a fundamentally new object. It's unique. There's nothing else like it. It is the manifestation of this background energy field of the universe. So actually understanding its properties in some depth is really important, and that's what we're doing at the Large Hadron Collider right now, and that will definitely happen. That will happen over the next 10 years. It's just that these projects take so long to build that we're already thinking, okay, but after that, what do we do next? And that's where it's not clear. That's where there's a real good, active scientific discussion to be had, and then a technological and a political discussion as well, because these projects are so big.
If you think of photons, and you can maybe wonder why we do not have a complex forms made from light. For example, if you have other particles such as electrons, atoms, they form complex structures. They form liquids, they form solids, and all our world around us are made from matter, which is basically quarks and leptons. But why we cannot make similar things with light? Lights are bosons, so in principle we could achieve a fluid of light, or even a superfluid of light, or maybe even a solid of light. So why that has not been possible so far? So one reason is that photons do not interact. Those particles The cross sections for the interaction between two photons is very small, and optical frequencies, in principle, the photons could interact via creation of electron-positron pairs, but in practice it doesn't happen because this process is extremely unlikely. So photons do not interact. That is one limitation why we cannot create a complex structures. Another limitation is that photons are massless. The rest mass of photons is zero. For any complex structure such as liquid or a solid to be built, this is a combination, this is a competition between kinetic and potential energy. So if photons don't have a mass and they don't interact, we don't have this notion and we cannot create more complex forms made of photons. However, this can be overcome nowadays, so we can cheat the nature and we can create artificially, we can give a photon a mass and we can give photons interaction. So how can we do that? So to give a photon a mass, it's enough to capture photons in one direction. If you have your photons, and if you can create mirrors such that the photons will not escape outside of the mirrors, there will be the motion will be frozen in one direction. There will only be possible to move into other direction perpendicular to those mirrors. Then effectively, in this two other direction, it will mean that the photons will be massive. The photons will have a mass. This mass will be finite, but it will be very small. So it will be of the order of 10 to the minus 9 of typical atoms. And this is actually quite useful because if the mass is very light, then any quantum effects which will appear at very high temperatures, even up to room temperatures. So we can fix the problem of the mass by capturing photons between two mirrors. The problem of interactions between photons can also be solved if you couple photons to something of the matter type, because if the photons will annihilate and create, let's say, an exciton in a medium, or if they will couple to some internal degrees of freedom inside an atom, for example, then via that other object, the photons will effectively interact. So this was possible to be achieved either in semiconductor structures with electron hole pairs, so excitons, or atoms placed in cavities where interactions between photons could be achieved by a coupling to these internal atomic degrees of freedom. So you could solve these two problems, the mass and the interaction between photons. And so because that was possible in experiments to be done, we could make photons interact inside that cavity. And in experiment, we were able to actually create a fluid of light. So interacting photons with a mass, which is very similar to any other fluid. And in particular, because the mass is so light, it was possible to achieve quantum effects, such as, for example, superfluidity at very high temperatures. So now we can step back a little bit and ask what is superfluidity. So superfluidity is a state of matter. It's a new state of matter where microscopic number of particles, a very large number of particles, form one object. They behave collectively, they behave together because they occupy the same state. So now, because each atom is not individual entity anymore, if the atoms start flowing, or if the photons now, in our case, we're talking about photonic superfluidity, start flowing, they will flow without any disturbance. They can, in case of liquid helium, for example, it's a famous example where they can flow up even a container and escape from the container. Or if they flow and they meet an obstacle in the middle of their flow, they will not scatter, they will not see the obstacle. So if we look far away from the obstacle, it will look as our superfluid is not having any resistance to anything, it doesn't see anything. So that was possible to be created for photons, coupling them to electron hole pairs in semiconductors forming polaritons. So once the quantum fluid was created, once the superfluid was created, it allowed injection of quite an interesting object there. We could put vortices inside such a superfluid. We could inject persistent currents into the superfluid. Observation of the frictionless flow was possible. So our photons were doing a very similar thing to what liquid helium or electron hole pairs in superconductors. So flowing without resistance, not seeing any obstacle on the way, and supporting persistent current, supporting vortices. So then we went a step further in experiments in various groups, looking at the transition between a normal state and the superfluid state in the case of these interacting photons. And it was possible to see that very similar, like for the matter particles, the transition between the normal and the superfluid state is happening via creation and annihilation of vortex-antivortex pairs, so binding and unbinding of those pairs. So in the same spirit as costless-Towless transition. So we already had our quantum fluid, which now can be used as a laboratory to explore quantum turbulence, to explore behavior of vortices, behavior of solitons there. But now we wanted to go one step further. So now we have a fluid, we have a superfluid. Why can we not create a solid out of light? And that's a very new area of research at the moment. We can do that because we can create a potential for light. Technologically, there are various ways of doing that. One can put some different pieces of a different material with different refractive index on the top of our mirrors, and giving effective potential for light. Or one can put a surface acoustic wave, so modulate the energy for photons via external sound waves. One can do very drastic things like etch micropillars. So instead of having two-dimensional structure, one can make one-dimensional lattices out of the semiconductor. So there are various ways of creating potentials for photons. And if now you place a photon which has a mass and interactions inside a potential, then you create something which is the same as in the case of solids. And why would we be interested in doing that? So as I said, the photons have very light mass, so the quantum effects are happening at very high temperatures. So now, by creating these artificial lattices for photons, we can try to model, we can try to quantum simulate some other materials which are much more complicated to study than photons. And moreover, this is already quite an active field in the area of ultra-cold atoms, but ultra-cold atoms have their limitations. Firstly, they have to be cooled to extremely low temperatures. Here, with polaritons, with photons, we can be almost at the room temperature. That's one advantage of that system. Another advantage is that the mirrors are never ideal, so there will always be some leakage of photons coming out of these cavities. And by capturing the photons and measuring their energy, their momentum, and their position, we know everything about the system inside. So we know not only the ground state, we know all the excitation spectrum of the system, which can be resolved in space. So the amount of information which is given in that system is by far much larger than the information which can be drawn from other platforms like ultra-cold atoms, for example. So at the moment, the photons inside those lattices are still in a so-called semi-classical level, which means that there is quite a large number of photons or polaritons inside one lattice side. So now the goal of the field, the open question of the field, which is mainly for experimentalists to solve, is how to make those lattices tight enough so that only one or a few photons can be placed in these lattices, so we can explore strongly correlated states with this platform. However, already, even without this tight confinement, already those photons in lattices or polaritons in lattices have been used to look at topological states. And in particular, you can imagine that if you create a lattice which is very similar to graphene, so honeycomb structure, lattice with a honeycomb structure, that what happens is that this materials, the graphene material, is a very interesting, has very interesting properties. It has a linear dispersion, the so-called Dirac cone, and the same was possible to achieve in the case of photons. And now, because one can also engineer a spin-orbit coupling in the case of these photonic systems, when we place this photonic system inside the magnetic field, it is possible to open a gap in the spectrum and then create the edge states which will be inside the gap. And what it means is that if you initiate a current going around, so let's say you have your lattice and you initiate a current which would a flow of these photonic particles, if you can achieve topologically protected state, it would mean that if you inject the current in one direction, even if it meets some obstacle, some dirt, some imperfection at the edge, it will just always flow around in one direction and will not flow in the other direction. There will be no scattering back. So these topologically protected states are quite of interest in the community for encoding information, let's say, in the direction of that flow. So basically, this photonic quantum fluids not only allow the realization of the superfluidity and the study of superfluid properties such as vortices, quantum turbulence, it's now moving into the area of quantum simulations where they can be placed in lattices and simulate hopefully strongly correlated states soon, but topological states already.
So one of the key aspects of understanding of how humans and climate and the Earth system interact that has become more and more important over the last 20 or 30 years has been human management or mismanagement, however you want to look at it, of the land surface. So how do we interact with vegetation? How do we manage the natural landscape and the sort of agricultural landscape for our benefit? Because that's what we do as humans. That tends to be what we do. We colonize new places and we utilize the resources that are available to us. We've always done that. That's what we're very good at. What we're not so good at is knowing when to stop and what the limits of that are and how to manage the impact of those things. That's partly because the dynamics of those things are very complicated. So one aspect where that has become very apparent over the last 30 or 40 years, or really since the advent of satellite observation, is how important forest deforestation and degradation have become. So we all know, the figures about how terrible deforestation is and how it's going on across different parts of the world. It's happening everywhere. So as an example, close to home here in the UK, we are one of the least forested areas in Western Europe. So about 12% to 14% of the UK is forest, but of that, the vast majority of it is planted coniferous woodland, so essentially commercial plantation forest that was planted mostly since the beginning of the 20th century, after the First World War, and in fact this is a little, sort of bit of historical context here that just shows some of the challenges that they're facing. So the UK isn't considered to be a forested landscape at all, and it isn't. It was. So if we go back 500-600 years to the pre-industrial revolution, so not that far, the majority of the landscape, particularly the lowlands in the UK, would have been covered with dense deciduous woodland. Lots of large animals, so there would have been wild boar, wolves, bears, and so on. That changed dramatically as populations increased and became more mobile, and deforested the landscape for timber primarily, but for firewood, timber and fuel. And then also to manage the landscape to clear for agriculture, so arable and cattle grazing. So all of these pressures on removing forest. it reached its lowest point. So the UK forest was down to a few percent cover by the end of the 19th century. And so when the First World War came along and the demands for timber were required for building trenches on the front lines of the First World War, essentially the UK ran out of timber for doing that. And so the government decided, look, we can't allow this to happen. If there's another war like this, we need to have timber to provide this. And so they established the Forestry Commission, whose job it was to make sure that the UK had enough timber, and that was by planting conifer forests. So I use this example of the sort of almost accidental deforestation that happened and degradation of the woodlands of the UK that happened gradually, then increasingly rapidly as the population increased and urban areas got bigger, to the point where when it suits us and we realise there's not enough woodland, then we decide, oh, it's gone too far, now we ought to do something about it. And the woodland in the UK has increased in cover quite a lot over the last, to the end of the 20th century. We're at the highest point for 500 years. But of that, very little of it is the same kind of woodland that would be recognisable 500 years ago. So in microcosm, that is a problem that's going on worldwide in terms of the encroachment into forests. So why is that important? It's important for a number of reasons. That globally, these forests store huge amounts of carbon. That carbon, if it's stored in the forest, it's not in the atmosphere. Deforestation and degradation, and I will separate those things. So deforestation is where you just cut the whole forest down and you take it out and you do whatever you're going to do with it. Most of the time you either use the higher quality timber, and then a lot of the lower quality timber either just gets left there or it gets used, some of it gets used for fuel wood and so on. So deforestation, and then degradation is the gradual encroachment onto forested environments. So that might be due to low-level agriculture, it might be to low-level clearing for woodland and for settlement. It might be due to building roads. If you build roads through forested areas and you increasingly fragment those forests, their value and their richness in terms of species changes dramatically because of connectivity. So, you start building a network of roads, you don't actually necessarily remove a vast amount of forest cover, but if you chop it up into smaller chunks that are cut by roads, then those chunks of forest become more and more isolated from each other in terms of seed dispersal, in terms of small mammals, birds, larger animals. And that has all sorts of implications for the resilience of those forests, how their response to fire, their response to drought, their response to all kinds of other stresses that are coming their way, partly as a result of us, partly a result of changing climate, which is also as a result of us, but for all sorts of reasons. So degradation is the sort of gradual lower intensity loss of forest, which the distinction between those two things is that one of the first question we want to answer is how much are we losing? And answering that question for deforestation, we do pretty well, because it's the sort of thing, again, that we can use satellite data to monitor, and we have done over the last 20 or 30 years. And there's been some really noticeable successes. So, for example, deforestation in the Amazon was approaching a peak in the 90s. Some of it was legal, was government exploitation of forest resources that were sold off to logging companies. Most of it was illegal logging, and it was very hard to track. And if you can't track it, it's very hard to prosecute people, it's very hard to legislate. The whole process requires you to have reliable information about where it's happening and as soon as possible after it happens. And so the Brazilian government actually took a very strong lead on this and developed their own satellite monitoring program, which allowed them to say where illegal logging was happening, when it was happening. And that sort of deforestation program enabled them, there has to be the political will to do something about it, but that also requires people to see, yes, it's happening here, it's happening on my backyard, somebody's taking forest that belongs to me, that belongs to us. And so when that happened, it was a lot easier for the Brazilian government to make those kind of political things stick. And that's what they did. And so they had a notable success in the 2000s, the late 2000s, in reducing deforestation. It's the one time anywhere, particularly in tropical regions, where politicians have managed to reduce deforestation. So I would sort of say that the more recent picture is perhaps not so optimistic. There's been an upswing again, but we can use satellite data to monitor deforestation and measure it pretty well. So if people decide to do something about it, we have the tools to do that. Degradation is a lot harder to spot because often you don't see these very obvious patterns that you get with deforestation, where whole chunks of forest are disappearing. That is much less obvious when there's low-level encroachment into forest, when there's clearance for agriculture, even when there's selective logging. So if you're an illegal logging operation, the sort of most stupid thing you could do is go in and just chop down a chunk of forest because it's obvious. So the thing you do is you go in and you pick the trees that will be most commercially valuable to you, you chop those down, and then you drag them hundreds of meters out of the forest to the nearest roads. In the process, you leave a gap in the canopy, and then you leave these trails through the forest, which are hugely destructive, but actually very difficult to see from satellite data. So degradation is a harder thing to map. It's across a much wider spectrum of forests. It's not just tropical forests as well. It's temperate forests, and it's in boreal forests as well. And so degradation is known to be a big cause of loss of forest in general, of reducing the quality of those forests for their resilience to climate, their value as an ecosystem service to us selfishly, but to all other organisms that depend on them. So there's been a lot of work again in trying to understand how we can map degradation rather than just purely deforestation. And there are UN-led activities in order to try and quantify those things. So the UN RED Plus, which is reducing emissions from deforestation and degradation, which recognises the fact that it's not just deforestation, it's degradation as well, and addressing those challenges will require, again, it will require political will to do something about it, but what politicians require is hard information that says, yes, this is happening, and we all agree that the methods that we're using to monitor these things are something that we can all sign up to. And that's not necessarily an easy thing to do, but again, satellite data are helping us to build those pictures that will then enable, global institutions to turn to politicians and say, if you want to do something about that, we have the tools to do that.
So my work is basically all about syntax, which is the way that we put words together to create meanings. And most people who do the kind of work that I do on syntax are really interested in the ways that languages vary when they do this. So, in English, you say, you put the verb and then you put the object. In Japanese, you put the object and the verb. In Russian, actually, you can put the object quite far away from the verb quite often. So languages vary in different kinds of ways. And people like me, syntacticians, we're interested in what the system is that humans have that does this variation. Right? So what is similar between an English speaker, a Russian speaker, a Chinese speaker, a Nungabuyu speaker in how we build sentences out of the basic bits and pieces we have? And the answers that people have given to that, and the answer that I believe is true, is that what is really similar is that we human beings have a capacity to take discrete units, like words or sounds, and we put them together in hierarchical ways. We put them together in chunks, and those chunks are put together in larger chunks, and those larger chunks are put together in larger chunks. And we do this in a sort of unbounded fashion. That is, we can just continue doing this, following the rules of our particular language, which is what makes our languages so creative. It's what enables me to say the sentences I'm saying just now. So this is a very important part of language: the discrete, the hierarchical, and the unbounded, the unending. And that's what most of my work's about. And that's what most people who do what I do work on. But actually there's more to language than this. So that is a fundamental aspect of the nature of language. But actually when people think about language, they think about more than just this aspect of it. There's something else. There's the way we use language, what we use language to do. We don't use language just to say literal things. We don't just, say, I am sitting on a chair. That would be pretty boring, right? what we do is we use language to express ourselves, we use it to express our thoughts, we use it to express how we're feeling, we use it to express what kind of a person we are. And that, I think, is another aspect of the nature of language that quite often gets lost from the perspective of people like me, who are focused very much on the theory of what human language really is, as far as syntax and grammar and things like that go. So I want to tell you a little bit about some work that I did with my colleagues at Queen Mary, which was about how the variation in language and the sense of self of particular individuals who speak language end up feeding into the kinds of grammatical rules that we have in a language. So this is work that has been done here in London, where we are right now, looking at the new kind of a language that emerges in teenage speak in certain areas of inner London. So if you go to somewhere like Hackney, Dalston, one of these areas of London, it's massively multilingual. So there's 100, and I'll probably forget the number, but there's hundreds of languages spoken in the borough of Hackney. And that means that through many immigrant populations, and that means that the children of these various speakers, they don't have a language which is effectively in common with each other, right? Because what they're doing is they're learning from their parents, whatever their home language is, plus some kind of second language version of English, right? So when they come to speak to other people, they're speaking quite differently from each other, right? So you've got some people whose parents might be from Turkey and who speak a sort of Turkish influenced version of English. You might have some people whose parents speak Haitian Creole and have a Creole variety. Some speakers who might come, who might have, some like Chinese and so on. So many different languages. So there's a question then. So what happens when you take all of these kids and you put them together? What kind of a language emerges? Is it just a hodgepodge? Is it just a mess? Or is it structured like all the other languages we know are structured into, particular grammatical rules? So you'll not be surprised probably that it's the latter. So the case I want to tell you about is something that my colleague Jenny Cheshire noticed when she was looking at the data of teenage speakers from Hackney. So what the team did was they collected loads and loads and loads of data and then analysed it statistically. And one of the things that Jenny was looking at is what's called a relative clause. So this is where I come in as a syntactician. So a relative clause is when you take a noun, like the cat, and then you add a clause after it. So you say the cat that I love, or the dog that jumped on me. So you've got these extra little bits, right? So the dog that jumped on me, that's the relative clause. So relative clauses in English, when they modify a noun which is human, so let's take something like the man or the woman, you say the woman who I saw, you can say the woman who I saw. You can also say the woman that I saw, you can say who or that, and you can also say the woman I saw. So 3 different ways of doing relative clauses, and they're all completely normal in day-to-day English, and everyone uses them in conversationally, just at a random in a kind of random collection of ways, when you have a human noun that you're talking about. So what Jenny noticed when she looked at this was that in the teenage speech of the children from Hackney, is that actually they were using it differently than speakers of other varieties of English do. As I said, those 3 kinds of relative clause introduction, who, that, and nothing, are not really, they're not really grammatically organized in standard varieties of English. There's some prescriptive norms. If you've got human, you should use a who. So second language speakers of English often get told that, but it's just not true. That's not what people do. People use that and they use who. So in standard English, you use all of them. But what Jenny noticed with or what our team noticed with the Hackney teenagers is that they began to use who when the noun, the person that the noun referred to, right? You've got a noun, refers to a person, when that person was an ongoing topic of the conversation, right? So if you imagine someone who's really important, or you're talking about someone who's really important to you, and you say, oh, that man I met at the party, or that man who I met at the party, and then you continue talking about him. He was this guy that turned up late and no one talked to him, and then when I saw him the next day, he gets talked about a lot. He's an ongoing topic, okay? Or you can imagine someone isn't an ongoing topic, right? Oh, those people in the bus, they were really upset when the bus blew up and something terrible happened and everyone ran away and da-da-da. But you don't talk about the people again, you're talking about something else. What Jenny noticed was that these Hackney teenagers were structuring the two kinds of relative clause in a completely different way than normal English. So they were using who when the noun was a topic of the ongoing discourse. So you can count the number of times that that noun is referred back to. And the more it's referred back to, the more likely it is that the person used who in their relative clause. Now it turns out it's even more interesting than this. So that's a new rule. It's not, I mean, no one taught the kids this, right? It's a new rule that they kind of worked out themselves, okay? Where did it come from? So that's a really interesting question. Now it turns out that in these various languages that are spoken by the kids that are not English, many languages have ways of expressing topicality. So, you know, Japanese does, for example, it uses a particular particle. Creoles do, they have a particular way of changing the verb. There's various kinds of ways that languages mark that something's a topic. English doesn't do that, right? Except for these Hackney kids. So what seems to have happened is that what these kids have done is it's like there's this floating feature around. It's like grammatical concept of topic that other languages are using, and it's not being used in English. And the kids, because they're not getting full input in English, they're getting second language English, what they're doing when they're talking to each other is reorganizing the way they're speaking and taking advantage of this kind of floating feature that's around, okay? And so they use that to organize their own grammar. And it turns out that it's even more specific than this. So the more multilingual and multi-ethnic you are, right? If you've got tons and tons of friends who all speak second languages, right? Then you're much more likely to use this grammatical rule, this new grammatical rule, than if you've got mainly, you know, monolingual friends. So it really turns out to be the case that, you know, it's in a sense an expression of your identity as a Hackney teenager, completely subconscious. You don't know you're doing this, right? But it expresses who you are when you start using this grammatical rule like that. So that's really interesting, I think, because what it shows is the emergence of a new rule, and that new rule emerges through social factors, right? It emerges through the ways that people interact with each other, the ways that they want to be close to each other, and it's done completely unconsciously. They don't know they're doing this. You can see it in the data if you look, right? You can see in the data that this new rule has appeared, but they don't know they're doing this. And that's how all language works, right? When I'm putting these sentences together right now, I don't know what rules I'm using to put them together. I just put them together and they work. And I'm not conscious of the rules. I can make myself conscious, and because I'm a linguist, I probably do know a lot of those rules, but people can speak perfectly well without knowing them. And what's happening in this group of Hackney teenagers is they've innovated. They've added a new rule into their system. And that is as much part of the nature of language, right? This creation of new grammatical rules from social factors as the very nature of the rules themselves.
So I'm mainly going to focus on freshwater security that comes from surface waters, from lakes and rivers, and I won't touch on groundwater because that has its own implications and problems in different parts of the world. Freshwater security is important in terms of, for example, what we call ecosystem services. So an ecosystem is where you have a group of microorganisms, plants, animals that live together in, for example, a water body, and they interact together with the chemistry and the climate, and that's the ecosystem. An ecosystem service is the benefit that ecosystem provides humanity for well-being. So for example, with lakes, They'll provide benefits in terms of fish for protein, for food, economy. They'll provide water for fresh water for drinking. Lakes also help to clean up water. They help regulate the carbon cycle. They help regulate climate change, etc. If we start to disrupt the ecosystem functioning of lakes and rivers, then we also pose major threats for freshwater security. So an excellent example of that is the Aral Sea, for example. So the Aral Sea was once the 4th largest lake in the world. It exists in the former Soviet Union between Kazakhstan and Uzbekistan. But then in the 1950s, the governments there thought that they would want to promote further cotton irrigation in the catchment of the Aral Sea. Now the Aral Sea exists and is it exists in the middle of the desert. So it's very sensitive to changes in precipitation. It's very sensitive to change evaporation and the rivers flowing into it especially. And so the 1950s and 1960s especially, water was diverted from the Aral Sea for the cotton irrigation. And that meant that less water is flowing into the Aral Sea itself because it's all going into the cotton plantations. So between 1960 and about 1980, the Aral Sea lost about 90% of its volume. So it shrunk to a really small size. And that meant that all the hundreds of species that lived there all died out. The Aral Sea shrunk to such an extent that it caused major health problems with local populations because they lost their fishing industry, basically. So the freshwater security that they had from the fishing industry, which was one of the biggest in the former Soviet Union, just disappeared within a matter of decades. This caused their health become compromised, which meant that they were much more susceptible to disease. And so again, we can see that's kind of a very extreme example of how human impact on lakes can really affect freshwater security. So the World Economic Forum have recognized that freshwater security is one of the most important concerns going into the future because of population increases around the world. We are making more demands on fresh water for both drinking, but also industry and factories, etc. But one of the problems is that fresh water itself is very unevenly distributed. So in North America, it has over half the world's fresh water, whereas Southeast Asia has only about sort of 10% of permanent surface fresh water. But 60% of the world's population live in Southeast Asia. So the demands there are very large and very extreme, and that's why it is of a great concern. So there's been some very nice studies done that have looked at freshwaters around the world, and it's estimated that at about any 1 month of the year, about 4 billion people are exposed to threatened freshwater security. And that's defined by, say, people taking water out of a river that's more than actually flowing through the river. And about 500 million people on the planet are exposed to very dangerous levels of freshwater security throughout the year. So we can see how it's an extremely important problem. Climate change is having some impact on that as well. Unusually, you might think that there's actually more fresh water in the world today than there was 30 years ago. As the volume is actually increasing, but is increasing in certain regions of the world which perhaps aren't needing it so much. And so again, that has kind of implications. One of the major things we're seeing with freshwater security now and into the future is linked to biodiversity. So freshwater covers about 3% of the surface of the land surface of the planet. Yet freshwaters contain 6% of the world's biodiversity. They contain over 1/3 of the world's vertebrates and over 40% of the world's fishes. So that means for actually a very small amount of area, they contain a very high proportion of biodiversity. And that makes freshwater security and biodiversity very, very important. There's been this really nice study done called the Living Planet Index that's done by the WWF, the World Wildlife Fund, and also the Zoological Society of London. And they've looked at tens of thousands of populations of thousands of species from 1970 up to the present day. And they use 1970 as a baseline. And what they found for freshwater vertebrates is that they've declined in population by over 83%. So 4/5 of the world's freshwater vertebrates have disappeared. These are the wild vertebrates. And if you think that we rely on these vertebrates for food, for recreation, for ecosystem health, that is really, really damaging. And so I think in terms of, things like pollution of lakes can damage freshwater security, but we can clean that up. We can clean that up through international legislation, for example, for acid rain. We can clean it up through local and regional legislation, for example, through farming impacts on lakes and rivers. But when we look to biodiversity, it's very hard to regain those populations. And if populations keep getting less and less, that means that they could go into extinction. And then when you lose a species to extinction, you're never going to get it back. And so there's been a lot of talk about whether the Earth in general is moving into a sixth mass extinction. We're going to be losing all these species. And in terms of population decline, and especially in fresh waters, that is not negating that hypothesis of the sixth mass extinction. So we could be moving towards this kind of like this sort of tipping point in the Earth. And that, in a sense, is why freshwater security is extremely important, not just for human health and well-being in terms of fresh water. It's important for biodiversity in general around the planet. Biodiversity is important for regulating carbon cycle, nitrogen cycle. So again, all these things in the planet are all interrelated and interconnected. And if you start damaging one to such an extent, then that will have impacts elsewhere in the world as well. So in the last 10 years, a lot of the research has been using, for example, remote sensing from satellites just to actually characterize where is the water and where is it disappearing from, and potentially where to. So some studies that have come out in the last couple of years have shown that there is a lot of freshwater decline, both from, for example, from the Greenland ice sheet, the Antarctic ice sheet, and that's linked to global warming and that ice melting into the oceans. But also a large amount of decline from, for example, Northeast Asia, some parts of Central America, southwestern United States. And this seems to be from agriculture. And we've got such intense agriculture there that you're using up all the fresh water that you can see changes in the gravity of the Earth from that. And that is, that is some of the sort of cutting edge research that's showing areas of real concern in the last couple of years.
So I was going to say a little bit about the idea of treating aging or anti-aging treatments. And this is a complex topic. Let me say, first of all, I think I should say this, which is that I'm all for that. I think we want that. And the reason why is because aging is fundamentally a horrible thing. In many ways, I think, it's part of the human condition which is almost maddening and somewhat similar. I say it to the students sometimes, to a situation where somebody comes to you and they tell you that, okay, in 20 years, some men are going to come and knock on your door in the middle of the night. They're going to take you away and they're going to torture you for about 2 years until you die. And that, that's pretty much our condition as human beings. And that's what happened to both my parents. I watched that happen to them as they were killed by diseases of aging. So aging is a horrendous thing. So in terms of the idea of treating aging, there are problems, I think, with thinking about what do you mean by treating aging? What is a treatment for aging? So I've argued that you can't really make a distinction between aging and aging-related disease, although sometimes people do. So a treatment for aging is a treatment for aging-related disease as well. So does that mean that having a coronary bypass operation or having a hip replacement operation, that's a treatment for aging. Is that an anti-aging treatment? That's not usually what people mean. I've also argued that there probably isn't a central mechanism of aging, although some of the work on the short-lived animal models like C. elegans gave the impression that that was the case. I think this was illusory, actually. So if there isn't a central mechanism of aging that you treat, and if there's not a difference between aging-related diseases and aging itself, what is an anti-aging treatment? What does it really mean? What I would propose as a sort of solution to this problem is actually a new definition of anti-aging treatment, which is to say that really, when you talk about anti-aging treatment, you're talking about treatments that are preventative. And that's partly to distinguish them from simply everything to do with any aging-related disease. It also kind of uses the anti-aging. You're essentially preventing them from happening in the first place. And it also acknowledges the fact that in the laboratory, this is what we can do. This is what we've learned. One of the things we've learned in the laboratory is that you can intervene and prevent or at least decelerate the appearance of aging-related diseases. This is very strong across the animal models. But by that definition, that would mean that, for example, things that affect even prevent one aspect of aging would be anti-aging treatments. So, for example, sunscreen to prevent UV radiation damage of skin. So that's part of aging. And you can use sunblock, and sunblock will prevent. It will delay and protect against that aspect of aging. So that's an anti-aging treatment. Or even if you go to the hygienist and you have the plaque taken away from your top of your teeth, and that prevents aging of your teeth, that's a preventative treatment of an aspect of aging. So that's an anti-aging treatment. In terms of the older notion of anti-aging treatment is something against the whole of aging. This is a really interesting topic. So in C. elegans, you can manipulate individual genes in C. elegans and see extraordinary increases in lifespan. You can double and triple and quadruple their lifespan. Even one group increased them up to tenfold. And an implication of that, this is what drew me into this field, was that there's some sort of extraordinary core processes of aging which underlie the whole of aging. And if you could understand that, you could do extraordinary things with human beings. You could have people living, you could slow aging right down and just stave off diseases of aging for many, many decades, Wonderful. But I think that notion was also consistent with some of the theories of aging that were predominant in the 90s, particularly like the oxidative damage theory. So there was a notion, people expressed the idea that if you could enhance maintenance processes within organisms, you could essentially control completely the accumulation of damage, and you could extend lifespan dramatically. So this is what people kind of thought they were doing. But I think more recently, it's become clear that the higher up the sort of the evolutionary ladder you go, from worms up to flies to mice to rhesus monkeys to humans, the less plasticity there seems to be with the less of a sort of innate plasticity there seems to be in aging. So one of the things which I think has been a big shock over the last years was the results of tests of an intervention called dietary restriction on rhesus monkeys. So this is an intervention which in rodents and many other short-lived animals slows aging down dramatically. So in mice and rats, you get 50% increase in lifespan, suppression of a whole range of aging-related diseases. And this was tested on rhesus monkeys, and the results were really quite disappointing. At most, the effects that were seen, the small effects, look as if they were rather likely to be rescue of harmful effects of overeating, which is not what you see in the rodents. It's something quite different. So I think that at the moment, it doesn't seem likely that there's any sort of magical plasticity that you can tap into in the way that you can for example, in C. elegans. However, things change very rapidly within the aging field, and that's one of the features of this field, which is rather marvelous if you're working in it. It's so unstable. Theories rise and fall very, very quickly. And something that's happened very recently, which is just incredible, is the development of recent findings in rodents looking at a particular type of cell called a senescent cell. This is a very particular type of cell that accumulates with age and has been shown to contribute to the generation of a whole range of different aging-related diseases, from multiple forms of cancer to cataracts to cardiovascular disease, many other kinds of pathology. And experimentally in the mouse, if you clear these cells, which you can do through complex genetic interventions, and you can now do it with a class of drugs that are called senolytic drugs, you get these remarkable effects on health. You get essentially a broad spectrum protection against diseases of aging. But the mice still get the diseases, they just get them later. So it isn't affecting the entire aging process, but what it is doing, it seems to be affecting, as it were, a cause of senescent multimorbidity. So it's an underlying cause of multiple diseases of aging. So this is something radical and exciting and quite different to the way that conventional medicine is generally looking at diseases of aging, which is to wait until people get the diseases and to study them individually in separate disciplinary silos, in oncology or cardiology or and so on. So this just looks wonderful, but it's in mice. So I think the prospects for this working in humans, personally I think it looks quite good, but we've been here before many times. So I think I'm not particularly optimistic about interventions that are going to have major effects in terms of adding many years to life or anything based on the technologies that are around at the moment. But I think the possibilities, for example, for senotherapy, these drugs that clear senescent cells, as an example of something that's come out of the experimental biology of aging, is very, very promising at the moment. I mean, I don't want to give the impression that I'm being pessimistic about the aging field. I mean, I think that in a way I feel both pessimistic and optimistic at the moment, because there were a number of elements of the field that looked extremely promising, like this huge plasticity in aging that you see in the short-lived animal models, the oxidative damage theory and the whole damage theory of aging, which as an intervention that was going to have dramatic effects, dietary restriction, which looks quite disappointing. And I think the thing which doesn't seem to be there is this natural plasticity in aging that you see in shorter-lived animals, in humans, at least in terms of the possibility of slowing aging down. And one of the recent results that I think is consistent with that is that the maximum lifespan for human beings worldwide for many, many years, for many decades, was increasing year on year. But it's actually hit a ceiling, it's plateaued. And it did that around about the year 2000. And it's even becoming clear that some of the very long-lived people, the real record holders worldwide, that a number of them may be essentially unreliable evidence. So, for example, it's recently been, a case has been made that a woman who was thought to be the oldest woman in the world, Jeanne Calment, was actually not actually Jeanne Calment, it was actually her daughter, who she switched identities with when her mother died. So on the other hand, I think if we kind of turn things upside down, one can make the case that that there is a plasticity in human aging, but it actually runs the other way, which is that you can accelerate aging in human beings. And that's something that very much seems to happen when people eat too much. So when people become very overweight, it would appear that the aging process is speeded up. So one possibility is that interventions that actually protect against aging in the short-lived animal models actually could be used as ways to prevent accelerated aging in people who are overweight. But in terms of optimism, the thing that really makes me optimistic is the possibility of really understanding aging. This is quite aside from what you can do with the knowledge, because that must be possible. And I think over the last years that the basic concepts of aging have changed so much, and they've sort of evolved and transformed so much, that we must be coming close to the point where we have the basic foundation of an understanding of aging. And that has to be the way forward to be able to see what can be done in terms of preventing late life disease and allowing people to live longer, healthier lives in the future.
I'm here to talk about cancer, and cancer means many different things to many different people. But the reality is that cancer is a disease of age, which means it predominantly affects older people, and we're all living a lot longer because of general improvements in our standard of living. So now 1 in 2 people get cancer. As well as age, there's many other causes of cancer. People can have family histories and genes that can cause cancers or lead to cancers. Heavy smoking and excessive alcohol consumption, obesity, and even having other diseases can lead to the development of cancers. And there are environmental hazards as well associated with cancer. Cancers can be rapidly proliferative and very, very dangerous, and cancers can be very slow growing as well. Often, detecting a cancer earlier is associated with a better outcome. So we have screening programs for diseases such as breast cancer, colon cancer, and cervical cancer, where we try and detect it in its earlier stages. But cancer means different things to different people. And people use terms such as tumours, or neoplasia, or uncontrollable growths. It used to have a stigma associated with it, so no one would talk about it. But now, as science advances, our health advances, and we have issues in society that have gone away, people, I think, are much freer to talk about cancer. We can often cure cancers, and some cancers are completely curable. The definition of cure means living to old age and dying of something else. Other cancers, particularly when cancers have spread, are not curable. In those cases, we try and keep the cancers under control so people live with them and don't die from them. And sometimes we use analogies such as diabetes or high blood pressure, where people live with these diseases and don't die of these diseases. In terms of treatment of cancer, there's many different types of treatment for cancer. Surgery is really important if it's detected early enough. I specialise in the use of drugs to treat cancers, medicines such as immunotherapies, which don't stimulate the immune system. They inhibit the inhibition of the immune system, because cancer can turn the immune system off. Other people use radiotherapy to treat cancers, and we describe the combination, for example, of surgery, radiotherapy, chemotherapy, immunotherapy, hormonal therapy, and all the different types of therapy and surgeries as a multidisciplinary approach, where we have a team approach to treating cancer. So even if we can't cure it, the aim is that people live with it for many, many years or longer. The idea is to personalise treatment. That means treating the right person with the right tumour at the right time with the right treatments, which is difficult from one individual to the next. It depends on individual factors such as what people want for themselves. And it depends on tumour factors such as whether you can use those treatments not just to improve quantity of life, but increase quality of life as well, because having one without another is not very useful. Developments in oncology, though, are occurring at supersonic speed. One reason I became an oncologist was to combine research and patient care, to link what we call the bench to the bedside, So nowadays, we're talking about personalization of treatment, which means treating the right person with the right tumor, with the right time, at the right time, with the right treatment. And I think of use of medicines, use of surgery, use of radiotherapy together to try and maximize the cure rate, and even if we can't do that, maximize survival with a good quality of life. But it should be a team approach amongst different doctors and healthcare professionals, along with treating a patient and their family. Something we're doing a lot more of these days with cancer is gene sequencing. Gene sequencing of both the tumor, the cancer itself, and our own bodies, and to understand that interaction. And by unraveling all of the DNA of our own bodies to try and understand why some cancers occur, and unraveling the DNA of the tumor, we can use what we call treatment based on genes that are abnormal, either in us or the cancer, and we know those treatments are associated with a much better outcome. By targeting treatment in these ways, we can really change the course of cancer. We still sometimes need to use chemotherapy. I sometimes think of a cancer cell like the London Underground subway tube map, and I'm trying to work out, is it Charing Cross and Victoria that isn't working, or Waterloo, East Acton, Chalk Farm, Camden and Embankment? And if we work out the subway stations that aren't working, we can use targeted therapies to attack those subway systems or those individual subway stations. Cancer cells are clever and they can find ways around that. They can find different routes. But it's great that we can now use targeted therapies which are much more precise, have fewer side effects, and patients do much better on them. And examples include things like the ALK inhibitors in lung cancer, or the anti-PD-1 or anti-PD-L1 immunotherapies. In patients for whom those are suitable, they really have transformed the life of people with cancer, such that in the old days, people used to die really rapidly from things like metastatic lung cancer and other diseases such as that. Nowadays, based on findings in the laboratory translated into people, we can really transform the lives of these people. So we now expect someone with metastatic melanoma, for example, to live more than 5 years with these remarkable drugs that aren't just focused on killing the cancer, but are focused on strengthening our own immune systems as well. We like to take a holistic approach, though, to treatment. It's not just about the drugs and the surgery and the radiotherapy. It's really important that patients are fit. They have the right diet. They have the right constitution. So quality of life goes hand in hand with quantity of life. Some cancers, though, don't cause many problems anyway. They can be very, very slow growing. And cancer is a bit of a marketing term. It's used to describe anything from a pancreatic cancer that can spread very rapidly through us, with survivals measurable in months, to a little skin cancer that's never going to cause a problem anyway. And so going forwards, it's really important, in conjunction with patients and their families, to understand the type of cancer someone has, so you can work out how best to treat it. And if you work out how best to treat it, we're usually prolonging survival as much as possible with a good quality of life. As an oncologist, every day I'm learning. I'm learning about people and their families, and I'm learning about cancer. If the road to really cure cancer is 1 mile long, we're probably 10 feet into it. I really don't understand how and why cancer spreads, or really, in a disease as simple as breast cancer, why it happens. For example, a woman may have 2 breasts, usually, the same family history, the same genes, but only one bit of one breast gets cancer, for example. Why that occurs, why it spreads to the locations it spreads in, the pattern of spread that we see, and really why our treatments don't eradicate all cancer cells. Why cancers can recur many, many years later. We know that cancer stem cells can exist, a bit like a queen bee. It can repopulate a nest 8, 10 years later. But what we really need to know, and what we really need to understand, is why cancers happen to some people and how best to treat them, to eradicate them. Because it's still a reality that once a cancer, such as breast, colon, prostate or lung cancer, the common cancers, once they've spread, we no longer consider them curable. And really what makes them incurable, why they're incurable, and what we can do to increase the cure rate are questions that I ask every single day.
Our next lecture is going to be about the speed prior, which is really useful for inductive inference. What is inductive inference about? There is data coming in and we can encode the incoming data in terms of bit string. All the videos, all the audio that is coming into a learning system can be encoded by some bit string X, let's call it X, and then at a given moment in time you have observed X, and then you want to predict the future, because machine learning is about predicting future things, unseen things from past experience. So the big question is now, given the X that I've seen so far, what is the future that I have to expect? And using Bayes' rule, what we can do is we can say, okay, let's look at the possible futures Y. So the entire life will be the combination of X and Y. And now the question is, what is the most likely Y that we can observe given the X that we already have seen? And then Bayes basically says the probability of Y coming after X, of X being followed by Y, is the same thing as is proportional to the a priori probability of X, Y taken together. And now Solomonov at some point in the 60s came up with an ingenious way of optimally predicting futures in such settings where the only assumption is that the X's and Y's are drawn from a computable probability distribution, and he had an uncomputable way of devising a universal prior, which is known as the universal Solomonov prior, and this universal prior dominates all computable priors in the sense that it assigns as much probability to any X as any computable prior, save for a constant factor which does not depend on the size of X or anything like that. Now, having said that, let me point out that Solomonov's optimal but non-computable method for inductive inference indeed assumes that observation sequences X are drawn from a recursive prior distribution, which is often called mu of X. Mu of X, that's the original prior distribution, which we don't know. So we don't know what is the rule that defines the new data coming in based on the old data that we have seen already. So instead of using the unknown mu of X, we predict using the celebrated universal innumerable prior, or sometimes called Solomonov-Levin semi-measure M of X, capital M of X, which for all X exceeds any recursive mu of X, which is the true distribution, which we don't know, save for this constant factor independent of X. By the way, Ray Solomonov was a visiting professor here in our lab in the early 2000s. Unfortunately, he passed away a couple of years later. Now, the simplicity measure M of X of Solomonov's universal prior naturally implements Occam's razor. Occam's razor says simple solutions are preferred over complex solutions, and this notion of simplicity is closely related to K of X, capital K of X, the Kolmogorov complexity or algorithmic information of X.
In fact, there's a close connection between m of x, so Lamanov's universal prior, and k of x, the Kolmogorov complexity of x. And my previous postdoc, Markus Hutter, has explored lots of these connections. Now, predictions based on m are optimal in a certain incomputable sense. However, m, this innumerable universal prior, assigns high probability to certain data x that are extremely hard to compute. So although these x's are really hard to compute, they get a lot of a priori probability assigned through this m of x. And this doesn't really match our intuitive notion of simplicity, because our intuitive notion of simplicity has something to do with the complexity associated with computing something from some other thing. So I suggested a more plausible measure, universal measure, derived from the fastest way of computing data. Not necessarily from the shortest way of computing data, the most compressed way, but the fastest. And in absence of any contrarian physical evidence, I assume that all of the physical world around us is generated by a computation, by a computational process, without any probabilistic interventions. No, just by a computer program that computes all of the data that's coming in, and that all possibly infinite sequences of observations are therefore computable in the limit. So this assumption is more radical and stronger than the one of Ray Solomonov, who just assumed that the distribution is computable. But in his case, you can have infinitely long histories of universes which cannot be computed by a finite program. And then what I did, I replaced Solomonov's measure m by the novel speed prior s, the speed prior s, under which the cumulative a priori probability of all data whose computation through an optimal algorithm requires more than order of n resources, and this order notation, asymptotic optimality or notation, more than O of n resources is 1 divided by n. So that's the speed prior. And to evaluate the plausibility of this, consider that most data generated on your own computer are computable within a few microseconds, and some of them take a few seconds, and a few data files take a couple of hours, and very few take days, etc., etc. So in that sense, the speed prior seems to be a quite reasonable way of translating resource limitations into a priori probabilities that should be used for inductive inference. If you don't predict the future through Solomonov's universal measure, but instead use the speed prior, then you get different types of predictions, more precise predictions. And let me immediately go to an extreme application. There is no physical evidence against the assumption that the entire history of our universe is computable through a finite program. And the most important goal of physics is to find that hopefully short program. And we assume that this program is sampled according to the speed prior, according to S, or according to some less dominant prior, which is dominated by the S prior, which corresponds to some suboptimal computation of the history. The legendary Konrad Zuse was the first scientist who seriously suggested that the universe, the entire universe, is being computed on a grid of computers, or a cellular automaton, as it is now called. Compare the related work by Ed Fredkin, who initiated the translation of Zuse's 1969 book on Rechnender Raum, on calculating space, where he presented this thesis. Now, under our assumptions of a computable universe, we can immediately predict, using the speed prior, that, first of all, our universe, as it is not going to get many times older than it is now. That's one interesting prediction. Then, another important prediction, large-scale quantum computation that everybody is hoping for, it is not going to work well. Maybe adiabatic and certain types of quantum computation that are about simulating quantum systems, they may work nicely, but the really desirable universal quantum computation that would be used to break cryptographic codes and everything, that is not going to work well, essentially because it would require too many computational resources in interfering parallel universes, and the speed prior would assign low complexity, low probability to that. And a third prediction is that any apparent randomness in any physical observation, such as beta decay, is in fact due not to true randomness, but to some yet unknown but fast pseudo-random generator, which we should try to discover. Maybe the pseudo-random generator is the short program that computes pi, the digits of pi. If you print them out, they look random, but they are not. Yes, every sequence of 3 numbers like 5, 9, 6 appears roughly once every 1,000 times. However, it is not really random because there's this very short program of pi that computes all of that. And the prediction is that everything that seems random at the moment is at some point going to turn out to be non-random and computed by a deterministic random number generator. These ideas have recently attracted a lot of attention, and you can read more about that in the paper on the speed prior, but also in the even older paper I wrote in 2000 on the algorithmic theories of everything, which then, as a spin-off, created the speed prior paper.